I'm Dr. Roger, and today we're looking at differential equations, in particular systems of first-order linear ordinary differential equations. I have a matrix equation here, x prime equals ax, where a is the matrix 2, negative 5, 1, negative 2, and I want a real valued solution. My initial values will be complex, so I'll have to continue from there. And to solve this, I need to find the eigenvalues, which is determinant of a minus lambda I equals 0. Eigenvalues are the values of lambda that make this true. A minus lambda I is 2, negative 5, 1, negative 2, minus lambda times 1, 0, 0, 1. And I want that determinant to be 0. So that's 2 minus lambda, negative 5, 1, negative 2 minus lambda, determinant equals 0. And the determinant of a 2 by 2 matrix is the product of the main diagonal minus the product of the off diagonal. So that would be lambda squared minus 2 lambda plus 2 lambda, those cancel, minus 4 and then minus negative 5 is minus 4 plus 5 is plus 1 equals 0. So lambda equals plus or minus I. Now that I have complex conjugate eigenvalues, I'm going to use lambda 1 equals positive I, substitute that in here as a matrix, 2 minus I, negative 5, 1, negative 2 minus I, times my eigenvector xi, xi1, xi2. I'm using the Greek version of x, xi, rather than x, because x is the actual solution. And that product equals the 0 vector. The second row gives me 1 times xi1 minus plus negative 2 minus I, xi2 equals 0. And if I choose xi2 equal 1, then xi1 equals 2 plus I. So my first eigenvector, I have lambda 1 equals I, and eigenvector 1 equals 2 plus I and 1. If I do the same thing to find my second eigenvector, I'll find that the eigenvector corresponding with a conjugate eigenvalue is the conjugate of the eigenvector. Let's do that. Lambda 2 equals negative I, so I have 2 minus negative I is 2 plus I, negative 5, 1, and negative 2 minus negative I is plus I. xi1, xi2 equals the 0 vector. The second row gives me 1 xi1 plus negative 2 plus I. xi2 equals 0. If I choose xi2 equals 1, then xi1 is 2 minus I, which is in fact the conjugate, so that gives us lambda 2 equals negative I, and eigenvector 2 equals 2 minus I and 1, the conjugate of the eigenvalue. Had I chosen to work with the first row, I would have arrived at eigenvector 1 equals 5 and 2 minus I, perhaps, because that gives me 5 times 2 minus I minus 5 times 2 minus I, and then its conjugate for the second eigenvalue. These turn out to be equivalent. They're multiples of each other, complex multiples, but still multiples. Now that I have eigenvalues and eigenvectors, I can write my solution. X is C1 e to the lambda 1t times eigenvector 1 plus C2 e to the lambda 2t times eigenvector 2. Rather ugly. I'm going to just choose C1 equals 1 and C2 equals 0 to make this easier to work with. So I have my solution X is Euler's formula for e to the it is cosine cosine t plus I sine t times 2 plus I and 1. So my solution X is multiplying this, it's 2 cosine t plus 2I sine t plus I cosine t plus I squared, which is negative 1, so minus sine t. And my second row is cosine t plus I sine t. So X has a real component, separating just the real into one vector, 2 cosine t minus sine t and cosine t. And then an imaginary component, I times 2 sine t plus cosine t and sine t. If these are both solutions, theory tells us that the real part is a solution. So one solution is 2 cosine t minus sine t, cosine t. And the imaginary part is also a solution. I'm going to call that x2, 2 sine t plus cosine t sine t. So our general solution is C1 x superscript 1 plus C2 x superscript 2. Any linear combination of these two solutions is also a solution. So my general solution is C1, 2 cosine t minus sine t, cosine t, plus C2, 2 sine t plus cosine t times sine t. And these may be hard to visualize. You can graph them on your calculator in parametric mode to see what the graph looks like. And you should be able to some extent, sketch what the solution looks like. If our eigenvalues had a non-zero real part, that would be down here as an exponential multiplied by these trig functions. And if the real part is positive, they will spiral out. If the real part is negative, they will spiral in. You can determine that from the sign of the real part, because if we take this periodic vector and multiply this by an exponential that's decreasing, our positions will decrease as t increases, even though the positions repeat in terms of just this vector, we're multiplying it by a decreasing constant. In the x1, x2 plane, these do not spiral outward, they do not spiral inward, they stay the same distance from the origin, or in the same distance range. At t equals 0, this one is at 1, 0. and if t is a small positive value, the x1 component is still positive near 1, and x2 is positive. So we are moving into quadrant 1, which means that these move in an orbit that may be circular or elliptical, in this case elliptical, that does something like this. What would it look like if I looked at the other solution, this solution, the x1 solution, at t equals pi over 2, which I'm going with pi over 2 because that'll make my cosine here 0. I have -1, 0, so I'm over here. If t is a small positive value, or I'm sorry, if t is slightly bigger than pi over 2, my cosine becomes a small negative number, and my sine is still near 1, so a negative number minus something close to 1 is still negative. So my x1 will be negative near 1, and my x2 will be the cosine of something just a little bigger than pi over 2, which is negative, so I'm moving into quadrant 3, so the direction of arrows I showed from here is the same as the direction over here. I spiral counterclockwise. And you should be able to figure out from your solution without using technology whether it spirals inward, outward, or remains the same distance, in this case same distance, and whether it spirals clockwise or counterclockwise by just finding a point that will be on the axes and asking yourself, from that t value, if t increases, which quadrant do you move into? So our solution was x equals c1 times our first solution plus c2 times our second solution, where our two solutions were the real part and the imaginary part of the solution we got from Euler's formula. Come back soon for my next systems of equations video. With differential equations, there's always more.